All right, next section. So next section must be quite important because there's two little stars around it. So yes, it is very important. I already mentioned this in the previous video, the link between the domain of a function and which limits should you be computing to better understand this function. So this section is just going to really formalize the ideas that I've already talked about. So we're going to define the important limits to compute on the function. And I find overall, and this is really my personal touch as a teacher, I find overall like calculus books kind of forget about this aspect. Like it's more about, hey, here's a function, compute the following limits, and there's kind of no points to them other than just learning the techniques behind the limit and forgetting like the true idea, which is we're studying functions. The first thing you do when you study a function is you compute the domain. But then when you have a point where the function is undefined, or if the function is defined for any large number or any large negative number, like how do you understand the behavior of a function around a point outside of the domain, or for very large inputs, positive or negative? So the next definition is really to me an important one, defining important limits for a function. So when you're studying a function algebraically, here are the important limits to define and compute. First, any open endpoints of the domain will correspond to an important limit, and this of course includes infinity and minus infinity, which is always of course open. And if you have a piecewise defined function, so a function that changes formula, it will be important to compute the important limits where the function is changing formula. So for example, if it's changing around 2, then you want to know what's happening before 2 and after 2. Okay, so any open endpoints of your domain, or if you have a change of equation, you look at before and after. So let's do some examples. All right, example. So here's a function, the square root of x squared plus 1 minus 1, all that divided by x squared. So first, let's find the domains. Again, here, the domain is always the first thing you're always going to do. So first, I see a denominator, so x squared. Of course, x squared is going to be equal to 0 if and only if x is 0. So if I'm writing that down, so we have a division by 0. So here, x squared is equal to 0. There's only one x value that will do this. So when x is equal to 0, so this means that x equal to 0 is not inside the domain. There's also a square root. So we have a square root of some algebraic expression. So we have the square root of some shit. So we want x squared plus 1 to be always bigger or equal than 0, but this will always be true because x squared, the minimum number, is 0. So here, there's no problem. So there's only one restriction here, and it's x equal to, x cannot be equal to 0. So that's the only restriction for the domain. So this means that the domain is everything but 0. And I find like the best way to see the open endpoints is to always write your your domain using interval notation. So anything but 0 is from minus infinity to 0, union 0 to infinity. So here, what do we have? We have 4 open endpoints. So I like to start with the numbers, but it really doesn't matter which one you do first. So me, I will start with the left side of 0, then the right side of 0. So it crashes at 0, so I want to understand what's going on. And then I'll check at what's going on at minus infinity, and then going to infinity. So 4 open endpoints, 4 important limits. So the next part, let's define and compute. Of course, right now we don't know how to compute, so we're just going to guess the important limits using the numerical approach. So here we go. So the first table that I need a table for a limit going to the left side of 0. I need another table for the right side of 0. I need also a table going to infinity, and I need a table, no, let's do minus infinity first, just so it does not matter here, since I've labeled minus infinity as 3. The order does not matter. What does matter is that you do all 4. Okay, so left side of 0, right side of 0 to minus infinity and plus infinity. Again, here you need to construct your own tables, including drawing the rectangles on the test. So left side of 0, so if I go left side, this is very similar to my previous example. I have minus 0.1. So here are 3 numbers that are close to 0, getting closer to 0 on the left side, so strictly less. So on the right side, I'll use 0.1, 0.01, and 0.001. Going to minus infinity, my classic minus 10, minus 100, minus 1,000. Going to plus infinity, well, plus 10, plus 100, plus 1,000. So I don't want to spend too much time just writing the evaluation here. So if we focus on the first table, so that's if you compute the value of the function at minus 0.1 and then minus 0.01 and then minus 0.01, you're going to get, boom, the following values. So 0.498, 0.49998, and then 0.4999998. So you see these numbers are very close to each other, getting closer to 0.5. So here we're guessing the limit on the left side of 0, and we're getting 0.5. So remember, it's crashing at 0, but as your graph is approaching 0 from the left side, you're going to get closer to 0.5. We'll need a hollow dot at height of 0.5 to illustrate that. And actually here, if we look at the outputs on the right side of 0, boom, you actually get the exact same thing. Again, here it's just a coincidence. Okay, so it's just, we have actually a symmetric function here. So when you're guessing the limit on the right side of 0, so right side of 0, sorry, you're getting 0.5 again. So here you'll need a hollow dot at 0.5. So it's the same hollow dot on both sides at height 0.5. You could have, in theory, different values, but in this case, we get the same thing. Now going to minus infinity, again here, I don't want to spend too much time, but if you replace x by minus 10 and then by minus 100 and minus 1,000, and make sure you understand how to compute these output. I'm just plugging, this is just an evaluation stuff. Okay, I'm not spending any time on this. So you evaluate your function f, you're going to get 0.09, 0.0099, 0.000999. So these numbers are getting closer and closer to 0. So as x gets bigger, so the limit as x goes to infinity, my guess is going to be that this is getting closer to 0. So this means that this function probably has a horizontal asymptote at 0. And then if you do the same thing going to infinity, I'm not sure if I said infinity or minus infinity, but actually we get the exact same numbers. So going to, sorry, I'm doing minus infinity first. I'm going to be too fast. Sorry. So that first guess here was for, oh my God. No. My first guess here was for minus infinity. Just forgot the minus sign here. So the third table was for minus infinity, not plus infinity. Sorry. Okay, it's the bear talking. And then my new table is the limit going to plus infinity, and we're guessing again that this is going to get to 0. So a couple of remarks here, a couple of conclusions that we can make. Let's do this in purple. So first, we have a hole with the first two limits. We have a hole at 0, 0.5. Why 0, 0.5? 0 because my x values are around 0, and the 0.5 is the y value from the guess of those limits. And because we're getting zeros for the limit at minus infinity and plus infinity, we actually have a horizontal asymptote at y equals 0, and we have another one on the extreme. So that was extreme left and now extreme right. So we're getting the same one. It's possible to have two different horizontal asymptotes. It's possible to also have two different holes, but because we we got the same value on the left and the right side. We'll just need one hole to illustrate these 2 points. All right, so we have domain, we have important limits computed. So let's move to the next part. So since we're familiar with sign table, let's construct the sign table, and let's use this also to better understand this function. So first, when you're constructing the sign table, you want to know where is it undefined and when is it 0. So it's going to be undefined when the denominator is equal to 0. So of course here, when you're looking for undefined, we already know that it's undefined when x is equal to 0. We already did that computation for the domain. What about the root here? When is it equal to 0? So this will be equal to 0 when x squared plus 1 minus 1 is equal to 0. If you do the math here, I will spare you the detail, but this is the same as the square root of x squared plus 1 is equal to 1. You square both sides, and you'll get again x squared is equal to 0. So the only way the numerator is equal to 0 is when x is equal to 0. So remember, undefined here, you get that one by looking at the denominator equal to 0. And for the roots, you're looking at the numerator equal to 0. But here we get the same value, denominator and numerator. When this happens, always go for denominator. So here we have only one important column at 0 where it's undefined. And then we want to know what's up before, minus infinity to 0, and what's up after, from 0 to infinity. So if you pick one x value, for example, if you compute f at -1, you can check that this will give you something positive. Again, here, make sure you do that. Actually, we don't need to do that. We already know from the table that when you plug negative values, you're getting positive numbers. So the sign table is very easy to fill up here. And if you compute, for example, f at 1 or f at 10, okay, so let's just do that. We already have the output at 10. We know it's 0.09, which is positive, so don't need to worry too much. So might as well just use those tables of outputs. So we know the function is always positive, strictly positive, except at 0 where it crashes. So that was for the sign table of the function f. And now this is for me like one of the precious moments. Let's combine everything together. So domain, important limits, and the sign table to draw a possible graph for our function. Pure excitement, pure excitement. So that's the next part. Okay, so part B. All right, so let's construct that famous graph. When you're drawing a graph, of course here we don't have a lot, just have the domain, important limits, and sign table. So there's a lot of possible answers. It's possible that the graph you're going to get could be different than the one I'm going to draw here. But when you're thinking about what you did compute, which is domain, important limits, and sign table, as long as the graph is consistent with these three points, you're going to get full marks. So the first thing is, we know the domain is everything but 0. So whatever you draw, okay, you better not have anything, okay, around 0. So here, let me just draw a straight line here. So here, you don't want anything, okay, on top of 0. We know the function is defined everywhere but on 0. So if you're drawing something that crosses that yellow region, you're not doing great. So now, before drawing the graph, what I like to do is first illustrate the important limits. So we know we have a hole at 0, 0.5. So if I'm drawing this, I'll do this in blue. So here I have a hole at 0, 0.5 using my scale here. So that's my hole. So the height of that hole is 0, 0.5, and I know my graph. So I know it's defined before and after, and it needs to connect to that hole. So that's the first bit I can draw here. I don't know what the rest looks like, but I know it connects here at 0, 0.5. That was because of the first important limit on the left side of 0 and the right important limit on the right side of 0. Then from the third and the fourth limit, we know that we have actually horizontal asymptotes. So if we have horizontal asymptotes, let's draw them. So we know we have one at y equals 0 going to minus infinity. So I'm just going to draw it. So that's y equal to 0. So that's the reason why we have an horizontal asymptote there. It's because of the third limit. We got 0, or again here we just guessed it. Okay, we just assume that this is the truth, but this is just guessing at this point. And we have another one at plus infinity, and it's also going to 0. So this is again y equal to 0, and we got that one using the information from the fourth limit. And then we know our limits are, so now as long as we draw something that is around 0.5, around 0, and going to 0 to minus infinity, and to 0 to plus infinity. And now if I think about the sign of that function, so we know it's going to be positive before and after 0. So you just need to draw something that is consistent with that information. It does not really matter what you draw, but because I know it needs to be 0 at minus infinity, I need to start there asymptotic. And I'm just going, as long as I stay positive here, I'm happy. So here we go. That's an example of a graph that is always positive. Okay, asymptotic to 0, and then reaching that hole. So same thing now on the positive side. So I have something that is very close to that horizontal asymptote, and I'm reaching that hole. Okay, so here we go. So here's an example of a graph. Okay, that is consistent with the domain computed in the first part. So I see here with the graph now in blue, so this is my potential graph for f of x. It's defined everywhere but at 0, so it's consistent with part A. What about the important limits? I can see, of course, I can see that on the left side it goes to 0.5, left side of 0. The right side it goes to 0 also. On going to infinity, it's getting closer to that horizontal asymptote y equals 0. Same thing for plus infinity. So all the important limits are good. And then of course, when you look at this graph, it's always above the x-axis. So it's consistent with the fact that the sign table, which is like positive between minus infinity and 0, and positive again between 0 to infinity. So a lot of information. Of course here, why is the graph shaped like that? I mean, it's actually the actual graph because I know it, but we will learn later with derivatives why is it increasing and then decreasing, and we'll talk about concavity. But right now your shape could be slightly different. You could go crazier and make some waves or whatever, but as long as the domain, the important limits, and the sign table is respected and your graph is consistent with these 3 points, you're going to be making me super happy.